We don't have any questions. That's good. So welcome to part B. Part B. So let's start with topological invariance. Okay. So a topological property P of a topological space X is said to be an invariant or topological property. By the way, I will throughout the crash course, sometimes I will use the word invariant, sometimes I will use topological property, depending, but they mean the same thing. Okay. Okay, so it's said to be P is a topological invariant or property if whenever X is homeomorphic to another topological space, let's call it Y, then that topological space also has property P. Okay, we'll see this more in a thing in concrete thing. So for example, let's just go through some simple example that most of you probably already familiar with. For example, in linear algebra, the dimension of a finite dimensional vector space is an invariant for the space, right? Remember, if you have if V is isomorphic to V prime, then it means the dimension of V primes equals n. Okay, so this means that the notion of dimension in linear algebra can help us classify finite dimensional vector spaces. So the moment you know that a vector space has dimension n, you don't need to waste time trying to build isomorphisms between them, because you know immediately that they are isomorphic. Okay, so the question is whether we can use topological invariance to help classify topological spaces. This is very important thing, useful thing, because as you will see, if those of you decide to dive deeper in topology, very often it's much easier to prove the existence of a topological invariant than checking directly whether there exists a homeomorphism between the two topological spaces. Okay, so by being able, even with the naked eye, to see two topological, to see some sort of a property that are intrinsic in two spaces, you can immediately say, okay, so it can help you classify the spaces. Okay, so the question is, based on just what I said, we'll go more into this in the next few slides for you to see more. Who thinks is Hausdorffness a topological property? So by that we mean if a topological space, so say for example, if X is Hausdorff, and suppose that Y is isomorphic to X, does it mean that Y is also Hausdorff? Who thinks Hausdorff is a topological property? Who agrees? Just a hint. It doesn't matter if you get it wrong in these things. It will make it a little bit more clear as we go along. Yes. Okay, so Bob is saying yes. Anyone else? Yes, Hausdorffness is a topological property indeed. I will leave that to you. That if X is isomorphic to Y and X is Hausdorff, then Y is also a Hausdorff space. Okay, and here's a tricky one that I will leave you for you to think. Maybe you can ping on Discord. What about metrizability? So if X is metrizable and X is isomorphic to Y, does that immediately means that Y is also metrizable? I'll leave. This is a little bit more trickier, but I'll leave that to think as a point of discussion. Okay. So here's in lecture. So let's do a quick test. So in lecture 2, when we talk about homeomorphism, we notice, for example, that the donut and or the torus and the cups are the same for topologists, right? Because you can continuously deform one into another without cutting or gluing, without cutting and gluing stuff, without making mess. Okay, so based on that, look at the cup, the cup and the torus. Is there anything you notice that doesn't change? any invariant. What invariant can you see with your naked eyes? This is actually one of the easiest invariants because we don't need the abstract tools like algebraic topology and these things to show it. Anyone wants to adventure? It doesn't matter if you get it wrong. Look at the cup. Look at the donuts. Okay, I'll give you a hint. I'll point the thing. It's a number of holes, right? Right? They have one. Each of them have one hole, right? So that's a topological invariant. There is a technical name for this. You will come to this in the manifold section. But yeah, the number of holes. This, for example, is the thing you can see here. This has one hole. Obviously, you can on the thing on the outside. You can go from one end to the other, right? So the number of holes is the invariant. So they all have one hole, right? Okay. So this is naked eye test. In reality, there are a lot of topological properties that you need a little bit more abstract tools in order to see them. This type of stuff, this is easy to see with the naked eye. Okay. Okay. So let's go to the notion of connected spaces. Okay. So we say a topological space is connected if it cannot be written as a union of two disjoint open sets. Okay. So if you look at the topology and X cannot be written like this, then we say that X is connected. Okay. So this is already telling you, again, this is where you already aware of this, that changing the topology might change this thing. If the topology is different, maybe X can be connected under one topology, and you change the topology, then it's no longer connected. So it's very important which topology that you pick. Okay. So another way to say this is that an equivalent way of defining or as a consequence of this is that X is connected if X and the empty set are the only clopen open sets. Okay, remember what a clopen means, right? A set that's both closed and open. Okay. So remember, you can have open set that are it's called open sets, but they are both open and closed in the topological sense. So if you don't want all that mess, what you need to do is to use connected topological spaces. Okay, life becomes a little bit easier for you. Okay, and as you can guess, the opposite of in this case, the opposite of connected is disconnected or not connected. Okay, in that case, that means that you can write X as a union of two open sets, two disjoint open sets. So if you can do this, it means that X is disconnected. So connectedness is a very important notion in topology because many examples of topological spaces that, for example, manifolds, for instance, many important class of manifolds that you deal with in physics or in other applied topics are connected connected spaces. Okay, so it's very important to understand, to see this thing, what's going on this. So my question now is again for you is whether connectedness is a topological property. Is it a topological invariant? Okay, in other words, if X is connected and X is homeomorphic to Y, is it also true that Y is connected? Who thinks? Just a hint. Give a hint. Whether connectedness is a topological invariant. Yes or no? Who thinks? Who agrees? Yes or no? Who disagrees? just a hint, because in reality, you have to prove these things, okay, to see true or not. But what does the thing, your first your gut feeling? Who thinks connectedness is a topological property without Googling? Yeah. Okay. So Amir thinks yes. So does Bob. Yeah. Anyone else wants to throw in the hat? Don't be afraid of getting it wrong. It's just the thing. I claim that you will see in a minute, you will have the answer. That's very interesting. Amir says simply due to homeomorphism. So you can already see that, yeah. So I assume that in your head, you already computed that, you already proved that if X is because of the homeomorphism, then Y is also. Okay. I claim you will be able to see this in one slide or two. Okay, so let's move on. And a notion is connected, the notion of a connected subset. So given a topological space, we say a subset is connected in X, so connected in respect to the topology, in X in respect to the topology, obviously. If it's induced subspace topology, remember being a subset of X means that you can use the existing topology in order to create the subspace topology. By now, you already know how to generate this, right? So when that happens, we say that the subset A is connected because the induced subspace topology is connected. Okay, and I have a very interesting challenge here: whether this interval 0 to 1/2 as a subset of R, where obviously R equipped with the standard topology is connected. Okay, I'll leave this as a challenge. And there you go. Here's a proposition that I was going to think. I was saying that will give you the answer is that if you have the answer whether connectedness is a topological invariant. Okay, so if you have two topological spaces X and Y, the claim is if X is connected and F is a continuous map from X to Y, then the image of X is also connected in Y, okay? So I hope there is no doubt now that connectedness is, because of this proposition, I hope you can already see that connectedness is a topological invariant. Okay. And here's another interesting proposition that I want to challenge you with. So consider two non-disjoint non-disjoint connected subsets of X. The claim is that their union is also connected. And also another challenge I want to give you is whether you can generalize this instead of obviously we have two non-disjoint subsets, connected subset. Whether you have a finitely many, you can prove the same thing. Okay. And another much more trickier question is whether, okay, so this is union. We are talking about union here, this proposition. What about intersection? Under what condition or conditions can we have the intersection of A and B is connected? I want you to go and scratch your head around this. Yeah. And finally, I have this connectedness challenge for you. So the first challenge is that if you have two topological spaces, X and Y, with the underlying topology is T1, T2, the product topology is also connected. So you can see connectedness has very nice property, just like Hausdorffness, for instance. The product of two Hausdorff spaces is also Hausdorff. So you have also the same here, connected, the product of two connected spaces is also connected, okay? So the question, the second challenge is this, to check whether this is also connected. This is equipped with subspace topology of the standard topology. The same with this. And I claim also, we also have sphere finally. This is a very interesting example also. And another thing I want to comment is next week when we cover path connected spaces, you will see that it gives you another tool, another powerful way of checking whether a space is connected, because every path connected space is connected. Very often is much more faster. It's easier to check whether a space is path connected. In that case, if it is, then it is connected. So yeah, but the opposite is not true. A connected doesn't need to be path connected. So if you are struggling to check some of these spaces are whether they are connected or not, maybe next week you will find it easy to come back to them by checking whether they are path connected. If they are path connected, then it follows that they are connected. Okay, but we'll come to that next week. Okay, so okay, that's it. I know we have like 10 minutes left before we go to the poll. Does anyone have any questions about this notion of connectedness? Yeah, I could have maybe covered the path connected, but I didn't want to make it too much for you. So it's against the philosophy of giving you small doses of stuff, right? To make it easy for you to think to, especially those of you new to these things, to study. Okay, so in that case, if there's no questions, please stay so you can complete the poll about when the next session should be. So again, as always, the slides will be available on the repository, and the replay will also be available on YouTube. Please join Discord. I really encourage you to join Discord and start having conversation with the people, connect with the people. Follow us on Twitter and social media, and yeah, that's it really. Let me just make the poll about the next session so you can decide if I can find it. Okay, so there's another poll now asking when would you like to the next lecture to be, whether Friday, August the 20th or August the 27th. Okay, please complete it. So at the moment we have 50-50. I need someone to break the tie. Okay, so 27 is ahead. Who else? Do we have more? Okay, do we have more? So I'm really asking, can you give an example that I could visualize? Yeah, I think in one of the exercises, it's already clear that, for example, there is a connectedness challenge. For example, an example, the sphere is connected. I can tell you that now. So I've spoiled it. So the question is, prove that it's connected. And the clue is in the name, connected. You can look at the sphere. What does sphere have that others might have? Connected. Okay, so anyone else want to vote? Okay, so thank you, George, for offering, George and Amir, for organizing this. I really encourage you to use Discord in order to do review stuff between you, because this is the only way, by going through the stuff with someone else. This is the only way you can, you can expand your knowledge, and also, don't feel intimidated if you get things wrong. It's part of learning. So join George and join Amir in the thing, in the review. I'm sure George will post on the thing on Discord. Okay, so unless someone else votes, it seems that it's like 60% wants it to be on the 27th of August. So yeah, so we make it to the 27th of August. Okay. As you can see, just before we go, I told you that we would finish on the hour. Let's go. Let me just go back to the thing. Okay, so as you can see, the next session will be the last session on this section. So we will, after that, we will start with manifold stuff. So in the next section, we will cover path connected spaces, this type of thing. We'll also cover, compactness, paracompactness, all these notions that we need before we get to manifolds. Okay, so the next session will be, you will have a lot of stuff, a lot of technical mumbo jumbo, covers, open covers, and all these type of stuff that you need. That's why today I wanted to make it a little bit easy for you, by not, for example, adding the path connectedness stuff to you. So we do that next in the first part of the next session. And then you have all these other notions that you have to wrap your head around, things like, covers, open covers, open refinements, all these type of stuff, compactness, paracompactness, because you need that in order to understand what a manifold is. So yeah, so well done to all of you, those of you stuck around, and as you can see, we are very close to our goal, which is really to to get into manifold section. Now, how much taste of differential geometry that you want, we will see. Like I was saying, like maybe we should cover tangent spaces, for instance, this type of thing. We should cover fiber bundles, all this. So these are all like they're not like pure topology stuff. Maybe the right word will be differential topology, but a lot of this stuff are more like lean towards a differential geometry. And for those of you like the physics guys who are interested in general relativity, for example, it's all useful stuff, very, very useful things. Or even those who are interested in things like gauge theory, for instance, those things will be very, very useful. So we will see how much. Maybe we can have. I don't know. I'll leave it up to you. How much taste of how much deeper you want to go into manifold sections. In reality, all I need you to do for the purpose of Lie theory is to know what a smooth manifold is. Okay, but after that, those of you if you want to some extra sessions to dive a little bit to taste a little bit of the flavor of the differential geometry and these things, we can do that too. So yeah, maybe I'll do a poll after. We'll see how the first two sessions on manifolds go. If it's too if you find it easy and it's going well and these things, yeah, maybe we can dive a little bit more. Okay, does anyone have any questions before we wrap up? Yeah. Yeah, that's a very interesting comment about George saying smooth is differential, but not necessarily the other way. So he's saying whether any differentiable is smooth. That's very interesting. I claim that you will be able to answer this when we get to the differentiable in structure on manifolds. Very interesting question. Okay, does anyone have any other question before we wrap up? Any comments? Okay, well, in that case, well, I see you in 2 weeks' time. We are getting closer to the manifolds. Okay, so yeah, well done for sticking around and going through all these sessions, because it's really necessary in order to to have like a little bit deeper understanding of these things. Okay, so thank you so much for joining me on this session, and I look forward to seeing you in 2 weeks' time. So have a good day and happy weekend.